This is a summary video for the second inorganic chemistry topic in AQA A-level Chemistry. The alkaline earth metals are found in group 2 of the periodic table, which is part of the S block, because all of these elements have their highest energy electrons in an S subshell. Each of the elements has 2 electrons in their outer shell, and therefore they make 2+ ions, which is important for you to remember when you're creating symbol equations involving them. For instance, if we had to write a chemical symbol equation with calcium hydroxide in there, it would be important to remember that calcium makes 2+ ions, and therefore we would need 2 hydroxide ions to balance it. Because the alkaline earth metals are metals, they conduct electricity and they also conduct heat. Being metals, the elements in group 2 have a giant metallic structure and are held together by strong metallic bonding. This means they consist of a regular giant lattice of positive cations surrounded by a sea of delocalized electrons. As we know from the bonding topic, the strength of this bond is determined by the charge density and the number of electrons contributed. All of the elements in group 2 have 2 valence electrons, which become delocalized, and their ions all have a 2+ charge. This means they have stronger metallic bonding than group 1, whose ions only have a single positive charge. But just like you saw with the alkali metals at GCSE, as you go down the group, that 2+ charge is spread over a wider area, and therefore the strength of the bond decreases, making calcium softer than magnesium, and so on. You could be asked to compare the physical properties of the alkaline earth metals to other metals, and in order to do this, we need to talk about their bonding. So why does calcium have a higher melting point than potassium? Well, this is because calcium ions have got a higher charge density. Or you could also say that they've got a greater charge or a smaller radius, both of which are going to add up to that higher charge density. Or you could just talk about the fact that they have more delocalized electrons, 2 per atom as opposed to 1 per atom for group 1. And so as a result of this, there's a stronger electrostatic force of attraction between those ions and the delocalized electrons. As you go down group 2 from beryllium to barium, the atomic radius gets larger. This is because the impact of adding another electron shell is much greater than the impact of the additional nuclear charge from the extra protons. Linked with this is the trend in first ionization energy. As you go down the group, the energy required to remove the first electron decreases, because the ions are getting bigger, and this means that there's a weaker force of attraction between that outer shell electron and the nucleus. The melting point also decreases as you go down the group, from about 1300 for beryllium down to about 700 for barium. Again, this links back to atomic radius. The atoms or cations are getting bigger, but there isn't any change in overall charge. They're all 2+ charge ions. And so that means that that charge is kind of more spread out. And so this means that overall the charge density decreases, and therefore the strength of the attraction from the ion to the electrons also decreases. A simple 2-mark exam question might ask you to recall the trend for one of these properties and then explain why that is the case. So if we're asked to state the trend in the atomic radius of the elements from magnesium to barium, we can say that those atoms are becoming larger, the atomic radius is growing. And the reason for that is that each time we're going down a period, we're adding another electron shell. Or you could be asked about the first ionization energies. So we know that as we go down the group, that first ionization energy is going to decrease. And this is why reactivity increases as we go down the group. The reason for that is that these atoms are becoming larger and have more shells, so that outer electron is in a higher energy level. And this means there's a weaker attraction between the nucleus and that outer electron, making it easier to lose. As with all metals, the group 2 metals get more reactive as you go down the group, because the outer shell electrons are more easily lost because they're further from the nucleus and they experience more shielding due to the greater number of shells. You need to be able to write equations for the reactions of group 2 with water, and in the case of magnesium there are different equations for steam and for liquid water. So for steam we're going to have our solid magnesium with our gaseous water, because it's steam, reacting to make magnesium oxide and hydrogen, and you're going to observe a bright white light, just as you do if you make magnesium oxide by putting magnesium in a Bunsen burner. Then when magnesium, calcium, strontium and barium react with liquid water, it's acting as an oxidizing agent. So the magnesium is going to react with liquid water to make magnesium hydroxide and also hydrogen gas. That magnesium hydroxide would be a solid because magnesium hydroxide is sparingly soluble, so it's not really going to go into the solution. We know it's a tiny bit soluble because the pH is going to change by a tiny amount, but not by nearly as much as we would see if we had, say, calcium hydroxide, which is soluble and therefore would have the state symbol AQ. Calcium hydroxide is a colourless solution, but you are also going to be able to see some bubbles or effervescence from the hydrogen gas. The group 2 hydroxides get more soluble as you go down the group, and we can identify this by looking at the impact on pH. As we've just mentioned, magnesium hydroxide is only sparingly soluble, so a solution of magnesium hydroxide might only have a pH of 8 or 9, compared to a solution of barium hydroxide, which could be as high as 13 or 14. In terms of their uses, magnesium hydroxide is put in indigestion tablets in order to neutralise excess stomach acid, and calcium hydroxide is used by farmers to neutralise acidic soils in the fields where they're growing crops. Now, in contrast to the hydroxides, sulfates get more soluble as you go up the group. So the one to remember is barium sulfate, which is used in barium meals. In other words, it's used as a radiographic contrast agent. So if you're trying to take an X-ray of someone's intestines, they eat the barium meal, and the barium sulfate will reflect their X-rays in the same way that bone would. It's safe to do this even though barium sulfate is incredibly toxic because it won't dissolve in the body's fluids and therefore it can't be taken in. Barium chloride is also used as a test for sulfate ions, so the barium ions from the barium chloride will combine together with any sulfate ions that are in a solution to make a white barium sulfate precipitate. When we do this test, we acidify it first, usually using hydrochloric acid, because that way we're only adding chloride ions, which are in the barium chloride anyway, and the reason we do that is to remove any carbonate ions, which would give a false positive in that they would also generate a white precipitate. We can also use this knowledge in reverse to test for the presence of barium or magnesium ions. So we know that barium sulfate is that white insoluble precipitate, and so if we suspect that we have some barium ions present, then we can test for them by adding a source of soluble sulfate ions. And the obvious way of doing this would be to add some sulfuric acid. Likewise, we know that magnesium hydroxide is also a white precipitate. So if we suspect that we have magnesium ions present, we can add a source of soluble hydroxide ions like sodium hydroxide, and if we see that white precipitate, that gives us an indication that magnesium may be present. Titanium is a really important metal because it's so lightweight, and so it's used for things like making jet planes. In order to extract it, we take an ore called rutile and heat this with chlorine and coke to turn titanium oxide into titanium chloride. And then the titanium chloride can be further reduced using magnesium, or in fact sodium, as a reducing agent, in other words, an electron donor. So you should be able to write symbol equations for that process as well. You could be asked to demonstrate that magnesium is the reducing agent by using oxidation states. So we know that chlorine, being in group 7, has an oxidation state of -1 when it's found in compounds. And so based on that, we can work out that titanium here has an oxidation state of +4 and magnesium has an oxidation state of +2. In their element forms, of course, they're both 0. And so if we then look, we can see that titanium is reduced from an oxidation state of +4 to 0, where magnesium is oxidised with an oxidation state of 0 rising to be 2. And as you know, a reducing agent is itself oxidised. Sulfur dioxide, which is responsible for sulfurous acid, which causes acid rain, can be removed from waste gases from a power station by an acid-base reaction with calcium oxide. Basically, we spray a slurry into the gases that contains these calcium-based compounds, and this removes the sulfur. Thanks very much for watching, and I hope you're now feeling a little bit more confident about this inorganic chemistry topic. If you did find this video useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.